Okay, so welcome to this lecture. This week I will be covering 3 topics. The first topic is you touched upon it on the last assignment with plotting, and plotting with a library called Matplotlib, which is the most commonly used library for plotting in Python. It's based on the same commands you have in MATLAB, but adapted for using Numpy arrays for plotting. I will also introduce you to CALFEM for Python, so the CALFEM version of Python. I will also briefly go through how you can access CALFEM for Python on your own computer. We have still some issues in the computer room to get CALFEM to Python to work there, but I have a solution for that as well. But it's important that you have it on your own computer as well. And then finally, I'm going to give you an overview into object-oriented programming. This is not a course in object-oriented programming. That is kind of a course by itself, so it's not. But I wanted to give an overview of how to use the object orientation in Python in this course, and how to create your own object types. So let's start with Matplotlib. This is a huge library. This has, many hundreds of different commands and tools for plotting. There are 2 parts of it. There is a base layer for really drawing on a really low level for drawing circles, different shapes. And then on top of that, there is a special library called pyplot that implements many of the commands in MATLAB in Python. They're easy to use. You basically give it input and some additional properties, and it will produce a plot. So if you're using it in a Jupyter notebook, like we are doing here, this command here will make sure that it's inline into our document here. So if you're using a Jupyter notebook, the plots will be interleaved with the Jupyter notebook as well. So importing Matplotlib, the common command you're using is this one here. So import Matplotlib and then this extension pyplot, and you usually abbreviate it with PLT. So just like we did with NumPy, you have this NP prefix. We use PLT as the prefix for our commands. So you don't have to type import matplotlib.pyplot before each command. So let's run this. So it's very easy to use. So if you just want to plot some numbers, you can send it a list. So here I plot 1, 5, 3, and 4. I use plt.plot and then plt.show. For Jupyter notebooks, it's not necessarily to use show, but if you're running your Python script standalone, you need to show your plots using the show command. So basically, just a simple line diagram. So Matplotlib can take any items where you can access using brackets. So I showed you this first example used normal Python lists. Quite okay to use that as well. You can use Numpy Arrays as well. So to do that, we first, of course, import the Numpy library. And then in MATLAB, you usually do a X range 0:0.01 : and then the end range. In Matplotlib and NumPy, we usually use this linspace here that creates a range from 0 to 2 pi, and I want 50 numbers here, and it creates an interpolation between those. And then we can use X as a range here, and then also print them out as well. So now you can see here that we get range X is from 0 to 2 pi, so it's included here. And then we get Y values as well. And then we can just do plot X, Y. So that will take the X for X values and Y for Y values and plot a line using that input. We got a nice sine wave like this. You can also change the attributes of the plot, and this is similar to what you do in MATLAB as well. So here you have the third argument here is the color, and if you want any circles or dash dots or stuff like that. So our row sets are red, and we want circles around the points. And here we have BO dots, that is, we want dashed line, double dashed. We have plus signs here as well. So this red circles with a line, or blue circles with a line between. You can have a blue line, dash line like that. You can have a blue line with pluses. Oh, sorry, no line, just blue pluses. So if you don't put a dash, it will not draw a line. And you can combine that to draw a line, green line with dashes at each point. So I don't know, most of you don't have computers here now, so I will skip this here. But this is an assignment you can do yourself. You can also, of course, have multiple series in the same plot. So in this case, I plot x equals to linspace, and then I create two function values arrays as well, y1 and y2. And then I just list, so they come in three, so x, y, and then the attributes, and the next series x, y, and its attribute like this. Oh, I forgot to run this one. Now you can see you have two series in the same plot. You can change properties in two ways. You can use the plot command line here and add named arguments here. So in this case, line width 4. That means it's we will plot a line with the line that is 4 in width. You also have a object-oriented way of setting properties here. So line width can also be using set_line width, and there are a lot of other parameters that can be set like this as well. And then you can show here. So in this case here, you can only specify line width or a single series. Here when you plot here, it returns two objects. Line 1 is the first series, line 2 is the second series, and you can set properties individually on these series. So in this case here, two lines with the same line width. Now we get two objects here, line 1 and line 2, which we can set different line widths to as well, like this. You can also use another. So if you have plot here, you can, instead of assigning individual series, you can get a list of series. Then you can use the plot set p command here for set properties to assign attributes on all of these series at the same time. So in this case, I will change the line width to on all series to 8 here. So now both of them are wide like that. You can also plot the multiple figure windows, and for this to work, you should probably run Matplotlib in Spider or standalone. Then you get two windows. In running it in a notebook like this, you will get two figures after each other here like this. So to create this different plot, you use figure and you give it a value which identifies your plot. So you can, so this is figure number 1, and then plot figure number 2, and then the commands after that command will all go to that figure you create. So that's this way you can create multiple figures. It's also possible to create subplots. What that means is that you can create multiple plots in a single window. And it's a bit tricky syntax here to use. So the argument here to subplot here. So first you create a figure, then you create subplot 2, 1, 1, and that means I want a plot that is 2 columns, 2 rows. I think it's first time gives the rows. So this is 2 rows and 1 column, and this is the first plot. So this 2 rows, 1 column, second plot. It's a bit odd. So 2, 1, 1 means the first 2 ones are the size of the plots, or the rows and columns, and the second one is the plot inside that one. So now we have single plot with 2 series on top of each other. You can do 1, 2, 1. That means that you have them column-wise instead. So then you get something like this. So you have multiple possibilities, and subplots is probably useful also when you're running in Windows. Decorating plots. So you can provide a label, X label and Y label using the X label command, Y label for Y label. So running this, you can see here I have X2, Y1 here that are added, and you have X here on the bottom here of the plot. Another nice thing with Matplotlib is you can actually insert formulas directly into the plot, and you can use, I don't know if everyone is familiar with LaTeX, it's a typesetting system. You can enter the formula here as a LaTeX formula. So dollar here means that start formula, and this means end formula, sin x fraction pi 2. And then you can add this to the plot directly, and it will display in math notation. So you can see here, you get this nice function here, sin x equals to pi divided by 2. You can also create annotations. What I mean with that is you can create arrows inside a plot, provide text. Here you put xy, where you start xy text, and then you can specify how the arrow property should be, how it should be centered in the plot as well. You should look at the links for the exact command properties here. So in this case, I have I provide text here at one position here, and then I provide, so the text is pi divided by 2, 0, 0. So the text is placed in the plot function value area. So coordinates here are actually plot coordinates. And also the arrow points to n pi divided by 2 and 1. So it points here, and it starts like this. You can also set the axis limits. So using the xlim command here, you can define where the x-axis starts and ends. I can set ylim also where the y-axis starts and ends. So now we zoomed into the plot. You can also change the scaling, so you can have log scaling here. Where does it go? Log scaling of the axis here. So I plotted the exponential function here, and it becomes a line here. There is a lot of other plots as well. So you can plot histograms using so not many of these here are just examples here. I will show you. I will not go through them too much in detail. There is a lot of examples on the web, on the website of Matplotlib. So basically, you can, if you don't want the plot, you look at the image and look, this is the kind of plot I want, and I go into the example, and you have the source code for that. So here I plot a histogram using the hist function here. I provide the x values and the number of bins I want to sort them into, and then I run, and I get something like this. I can do bar charts. classic in diagrams. So here I provide X and Y data, and then just it plots the bars for each area using the bar command here. You can do scatter plots. So basically you can plot positions X and Y. You can provide colors for each point and also the scaling of the point. So you can change the size, can provide it as an array. You can also provide the colors as an array. Here you also see you can use the use of legend here to provide a legend of the data coming in. And that is described here. The colors are in the legend here. Here's also a grid command for displaying a grid in the plot. Contour plots is also nice when you want to plot a function space. So in this case, I define a function space here. First, I define the X range here going from -6 to 6 using 100 points, and Y going from -6 to 6. And then I use a special command mesh grid here to create the function space here. So X and Y will be used in the plotting. Then you can use them here to create the C space here, which is a function of X and Y. And then you give X, Y, and Z to the contour function here. And then it's here you plot a contour plot. So you have the first one is a colored contour plot, and the other one is a contour plot with lines. So this is a fill contour plot, and this is a line contour plot. And here you can see at which lines you have lines here, which values you have lines in the contour plot. You can also display images. So in this case here, I download a file from the web. And then I can use the imread command to read this image. And then I can use imshow to display the image. And now I don't have any access, but you can have access as well. So if I do access on here, it will also plot the actual. You can see the pixel sizes here in the axis here. So it's something like 1200 high and 1800 wide. When you have images, you can also choose the filtering of the images here, how the images should be interpolated, if it's zoomed in or zoomed out. I think it's better just to show that one here. So if you have an image here, you can set the filtering. If you don't want to show it pixelated, you can select the filter here to interpolate so you get a more smoother image. You can do streamline plots. If you have flow points. And then you can do bar chart I showed you here, 3D plots as well. So, CALFEM for Python. So most of you have probably used CALFEM in some way in MATLAB. And because this course in programming uses Python, we had a problem at some point a couple of years ago, so that we kind of focus on the developing of finite element code instead of writing all the commands yourself. So we decided to implement a subset of CALFEM in Python. And that project has grown over, I think, 4 master thesis works, and also a lot of work that I provided into a very comprehensible toolkit that is about 95% of the functionality of CALFEM currently. The difference is that we use, instead of using MATLAB arrays, we use Numpy arrays. We have also added a lot more mesh functionality to this version, and this is something that differs from the MATLAB version of CALFEM. There is one measure in MATLAB. Here we have 2 measures and also a lot of routines for generating geometry, defining geometry, which we then generate meshes. I will come to that later on as well. We also a lot of routines for plotting using Matplotlib that are specially designed for CALFEM to plot meshes and results on meshes. CALFEM is a bit in MATLAB. You just add CALFEM to the search path of MATLAB. There is no module hierarchy, but in CALFEM we decided to divide up the functionality in several modules here. So you have here the CALFEM core contains all the element routines and also some of the system routines like Solvec and routines like this. We have a utils module that contains the IO routines. One module that is called MISC. Oh, sorry, it contains some other routines that are not kind of found some other place in other modules here. Then we have an important here called geometry, which I'll go through next week. How to define geometry for meshing. And then we have a mesh module here that contains routines for generating finite element meshes. And then we have visualization modules here called VSMN20. That is the MATLAB version of the plotting routines in CALFEM. We also have a routine called VS, only VS here, but that is an older one that we have moved away from, which is another plotting toolkit called VisVis. So these are the routines that we have created. Those are all implemented as modules, just like Numpy. So let's see here. So if you are on a Windows machine or a Mac machine, to install CALFEM, you open an Anaconda prompt and you type pip install CALFEM Python. I don't think you have to install IQT5. That comes automatically now, so I will remove this from this. And if you run this command, it will install all the necessary packages that you need for Python or for using CALFEM. No, it's part of the Python package index. So the pip commands are part of a special another repository. So it's available so if you open a command, you can type pip and then you install that, and that will download from the web. So unfortunately, it's a bit complicated to get into the Conda package repository. So that's why I've chosen to use pip instead. It's basically the same functionality. Usually the pip libraries are a bit less mature. They got more problems with them, but. So now we have CALFEM downloaded and should be available to us here in our notebook. So not just this probably is a repetition for some of you. So I will just go through the general procedure for finite element calculations. So first you define the model, you generate the element matrices, you assemble the element matrix into global stiffness matrix, you solve the system equations, and then you calculate the element forces. So you probably have seen this. This is part of the CALFEM manual. So we will kind of do the same examples, but using CALFEM for Python instead. So first we have to import our module. So of course we need Numpy. So we import that as NP, and then we need the CALFEM core routine. So CALFEM.core CFC. We need a CALFEM vis.mpl, and we call it CFB. So this is the chosen prefix we have chosen for the different modules here to make it easier to write them. So you don't have to do CALFEM.core.asset, for example. You can just CFC asset. So first we define our topology. And here we notice our first difference from CALFEM. We don't use the first column in the EDOF matrix for numbering elements. So we just define the topology directly here. And here we also make a break from the Python convention here of numbering indexes. So the degrees of freedoms are numbers starting from 1. So we have the same numbering as in CALFEM for MATLAB. So that's why 1, 2, 2, 3, 2, 3. Those are actually the degrees of freedom here with the numbering correctly here. So let's import that one. Now we do define the EDOF. You can see here that is our EDOF matrix. Then we define our stiffness matrix. So we use the zeros command here to create a 3x3 stiffness matrix and a force vector that is 3x1. I should clear the output here. Then we just define some constants. So it's the spring stiffness. And then we define our elements here. So this is the way it's very similar to what you do in CALFEM for MATLAB. So CFC spring 1E, and then we provide our element properties. And we get, in return, we get an array with our element stiffness matrix. So we get two stiffness matrices here, element matrices, and they seem to be correct. One is twice as stiff as the other one. Then we assemble our element matrix into the global stiffness matrix, and here is a bit different from MATLAB. So in MATLAB, you have the left side here where you repeatedly assign to the global stiffness matrix. We use the fact that NumPy can modify values in place. So in this case here, we provide a K array, and ASM will modify this array inside here. It will assemble in KE2 into this one here, and use the topology here from the row number 0 and all the columns here. So in this case here, we need to use Python indexing. It's only the degrees of freedom that we use the same notation as in CALFEM. So in this case, this is first row, second row, third row. So let's see if we get something that looks reasonable. Yeah, looks kind of okay. Next, we need to solve our equation system. And we have create our boundary conditions here. 1 and 3 should be fixed. Here as well, we have to think about the indexing again. So, every time you index a array in Python, you can't use the degree of freedom number here. So this is the actual degree of freedom 2. And I assign that to 200 here. Then we have solve command, which is very similar to the MATLAB command as well. You take the global stiffness, the force vector, and the boundary conditions. So the boundary conditions here is the degrees of freedom. And if you don't specify anymore, they are assumed to be 0. So they're prescribed to be 0. You can add another array here with actual values as well. But this is a simplification. Then you get the displacements and the reaction forces here on the left side. This is how would you use the correct form here. I think this should work. So the final part is we extract the element forces. And then we need first to extract the element displacement for each of the elements. And that is done using the extract LDisp here with the degrees of freedom and then the global displacements. And then we calculate the forces here using the spring1s command. So it's the same structure as in CALFEM. You have the spring1e to create the element array, and then you have a spring1s to calculate the element forces. So the next example is bars. So this is also from the manual. You have fixed bars that are fixed to 3 positions here. So x, y, 0, here, here, and here. Then we have a force acting on this node here, downward. And then we have the degrees of freedom here, 1, 2, 3, 4, 5, 6, 7, 8. So we define our element topology again. We define our stiffening matrix. In this case, it's 8 by 8, and then we have a force vector that is 8 by 1. We define our element properties. We have different areas on the different bars here, Young's modulus, and then we have the element properties here. In this case, is E, comma the area here, and it's perfectly okay to use lists in element properties instead of arrays. You can, because they are so small, it doesn't matter. So you can just send them over to the command. In this case here, we also defined the element coordinates here using EX1, 2, and 3, and then EY 1, 2, and 3. And then we have the bar2e command that takes element coordinates x, EX, and EY, and then have element properties as a third parameter. And we create KE1, KE2, and KE3. We assemble the stiffness matrix. And then we solve the equation system here. And now we specify here that the boundary conditions 1, 2, 3, 4, 5, 6, 7 should be 0. We have at degree of freedom number 6, we have force 80,000 newtons pointing down. And then we use the solver command again. And now we see here that we have reaction forces at where we have prescribed positions, and we have displacement here at where we have the force. And then we do extract LDISP. And we have bar2s here as well, that takes the element displacement as input as well. And then we calculate our forces here. I will stop here and we take a 15-minute break. So now we're going to do a bit more complicated example. So it's called more bars. And we have, this is also from the CALFEM examples in the manual. So we have a lot of bars here with more complicated topology. We have a force acting in a 30-degree angle. We have all the bars have the area 25 and the Young's modulus here, and then are fixed on the left side here in X and Y direction. Here is the topology. So now we have a larger element of matrix. We have a stiffness matrix that is 12 by 12 and a force vector 12 by 1. We define some parameters here that we will use later on, and define the element properties as E, A. We have element X coordinates here for all our elements and Y coordinates. But now it starts to get complicated. If you should do all this assembly using a single line commands, this is kind of not so very useful for us. We need a way to assemble more efficiently the stiffness matrix. So what we do now is we loop over our element coordinates in X direction, element Y coordinates, and our element topology matrix array. And we use this zip command here, which will extract these ones and provide a tuple here with 3 elements in. So we have element X for the current element's X coordinates, the current element Y coordinates, the current element's topology. So we get kind of small arrays that we can use in our command here. Then we do bar2e, ELX, EOY, and EP. And EP is the same for everybody, so we can just provide the same element properties as the last parameter here. We do ASM element topo here, K, K. So now we have a compact loop that we can reuse for assembling any element structure. So let's run this. We have to define our boundary conditions. 1, 2, 3, and 4. Those are 0. We have 11, 12. We have our force acting in 30-degree angle. We solve our equation system. And then we have, I'm going to fix this live here. Now we have the same situation with element forces here. So we extract the element forces using the extract ldist command. We create an array for storing our element forces. In this case, there are just the force in each element. And we use, we create it in the same shape as our EDOF matrix. So shape the number of elements here. We also create the same size of n. And then we loop over again our, but now we loop over element displacements as well. So we have element x, element y, element displacements. We assign ni equals to bar to s, elx, ey, ep, and eld. And then we loop over and we get our element forces like this. So this is the way you should implement this all. You should have loops for assembly, loops for extracting the elements. And this becomes more important when you're then going to use a mesh generator, because the mesh generation will produce thousands of elements for you. So you can't do it by hand. You need to loop over the structures. So now we have a even more complex the one here. Here we have a mixed bag of bars and also of beams in a single structure. We have a force acting on the structure here on the left. And now we have, I think it's 18 degrees of freedom as max. And we also have rotational degrees of freedom here at each point. So in this case, we were going to use a bit different approach here. We are going to use a coordinate array and coordinate topology. Coordinate array, and here we specify the degrees of freedom for each node. And then we have degrees of freedom 1 here, that is for the beams, and degrees of freedom 2, that is for the bars, because they don't connect to rotational degrees of freedom. Then we define our element properties. Then our element EDOF1, that is for the beams. And then we have EDOF2 is for the bars. I don't know why they should have different properties here, but ignore that for the moment. Then we use a command called coord extract, which will create the element coordinate arrays. So EX1, EX2, those are for the beams. EX2, EY2, that is for the bars. And here now we have to have 2 loops because we have different element types here. So the first loop, we loop over the element topology for our beams. And we use beam2e, elx, ey, ep1. Assemble here, and then we do the same thing here, ey, using the topology for the bars. And we use the bar2e command here and assemble it as well. And then we solve our equation system the same way like this.
One question regarding the function assemble. In Matlab, it has 2 outcomes. You can also assemble the boundary forces.
Yes, I think you can do it here as well. So okay. I have this example doesn't show that part. So we have there is no element forces in this case.
Yeah, but if you're dealing with solid elements, then you have to integrate the force of the area of the surface of the element.
Yeah, I think you can take the element force as well. and use that in the, so it has the same parameters. So that is basically how you use CALFEM. And I've seen that you have problems installing it. Hopefully we can solve that tomorrow morning. But we had, so in this, so I will show you the assignment for this week is before I go to the object-oriented part. So now the actual assignments are a bit, I will open it up here. So there should be an English version of this one as well, assignment 2 English. So what we're going to do is in this first assignment is to, if we go to the bottom part here, you can choose 3 types of analysis. You have plate elements, you have 2-dimensional heat flow elements, and you have groundwater flow. So you have to pick one domain, and you will use that domain in the entire. You can also see which elements here you can use, plan TA, plan TS, and you use that for the entire assignment. And what we're going to do is first create a class for input data. You will also create a class for storing the results. You will create a class for solving the problem, and a report class. And in the first example here, the problems that you should implement are 4 elements. Why? So we will not do any net mesh generation in this assignment. It will only be to implement a very simple problem consisting of 4 elements that should be assembled together for each of the problems, just to make sure that your solver works and it produces sane results. Because when we move on to the mesh generation, you will need to make sure that your solver works for the small problem before you go to the large problem. So I will just continue to. Wrong. So this final part of the lecture, I will talk a little bit about object-oriented programming. And as you have probably heard from me, you have already been using objects all the time, because objects in Python are any data type in Python is an object, and every object has certain methods you can call them. So what are objects? So it's a concept where you combine data and methods into one single entity, and usually they describe nouns such as point, circle, equation, model, or square. And you interact with objects by sending messages to them. And the messages are the verbs. Sometimes the messages, they're also called methods. So which are the verbs which you can talk to the objects with. So if you have a circle, you can tell it to move, circle.move. Move is a verb. And it's also a method that you call. And when we looked at the strings, for example, yesterday, we called a verb called split. That is a verb on the string object, which splits it into several pieces. So it's a combination. So the string is a data type, containing data, but it's also an object that has a lot of verbs that you can interact with. You should also have something called properties that are attributes that can be links to other objects, but can also be values. For example, in the input data model that you will define, you can have the Young's modulus as an attribute to the object. And the blueprint for an object is described in something called a class. So the class is not an object in itself. Class is a blueprint for creating objects. So basically, it's a stamp where you can stamp out new objects. And the class describes how that object should look and be described. Before object orientation, and even today, many codes are written in function-based programming. So all functionality in your code is defined by functions. So for example, if you have a point, you can create a point, and that function will return a data structure containing x and y. If you want to move that point, you have to pass that data structure into the function, and the function can work on that data type and move it. You can zero the point, you can set the point, and you can also print the point. But there is no connection. The point in itself is just a list of two coordinates. There is no relation to an object or anything. It's just a data. And then you have functions that expect the data to be of a certain kind, and then you operate on these using this on this data structure using the function. So this is what function-oriented programming is, that you have a data structure that is separate from the actual functionality of your code. So the functionality is in the function, the data is in the data objects, and they are separate. And in object orientation, you combine these two together. So I can just run this as well. So I define my functions, and here you see I can create a point using the create point function. I print the point, I can move the point, and I can print the point. But the point itself is just a list. So if I just do p here, it's just a list of two numbers. It's nothing more. It's the functions that defines the functionality that you can do on that data structure, but they are separate. So the actual p is not part of the functions. That they don't know about p. They just expect that the first parameter is something that they can know how to manipulate. Classes. So if you want to create a class that describes an object, you use the data reserve word class, and then after the class you set a name for your object blueprint itself. So in this case, I want to create a point object type. The first thing you need to do when you define a class is define something called this range here, init here. And this is also called something called a constructor. It's a function that is called every time you create a new object. So for example, when you create a string, s equals to a string something, the string class has an init method that is called every time you create a new object. In this case here, the first thing we will do is to create x and y attributes connected to the object. This here is a strange kind of, looks strange. So self is a variable that contains a reference to the object created. If you want to create a blueprint, you don't have the actual object. You need something that can replace the object or stand in for the object to be described as functionality. And self, that will, when you run the code, will actually point to the actual object itself. So what we do here is that we attach an x variable to our own object here and assign it to 0. Same thing here, we create self.y and assign it to 0. Now that is connected to the object. And it's also called instance attributes. And those will be, every object will have their own x and y. Those are unique for each object you create. And an instance is also the same thing as an object. So the object is the actual data you create in your computer that represents that you actually use. So let's run here and define a point class, and then we'll create point objects. And now it's just like creating variables in Python. So we say p equals to point. That will create a new point instance from the class definition. And Q will also be an object of type of the class point. And now we can see if we run this, you can see here that both P and Q has X and Y attributes, which both are 0, because when you create a new object, init will be called and X and Y will be assigned to 0. You can change them individually, so X and Y on the P object are unique from the Q. So now when we change it on P, it does not change on Q. Another important aspect of it is something called encapsulation. One of the things that one often pushes in object orientation, that the user should not directly manipulate the variables and attributes of an object. So in this case, the attributes X and Y should be encapsulated in the class so that you don't access them directly. And I will show you later on that you can implement encapsulation and still have this easy way of using X and Y attributes. But let's start to just implement it the correct way. So you don't want X and Y to be visible from the outside. And what you can do to hide variables in Python is if you put 2 underscores before the variable name, it can't be accessed from the outside. So we pass in X and Y and assign those hidden attributes internally in our class. This will still work, so we can still create a point, no problem. What happens now when we run this? I don't think Python will be happy. No, because we hid away the attribute X. So those are hidden. We can't access them. We can't even access the if we type them like this. Those are really hidden, so they're actually not visible from the outside. And that's the idea. We want to protect the implementation of a class internally. So that is also called our private variable. So to be able to work with an object, we need to create methods for accessing this internal variables. So we create a set X that will assign the internal variable, set Y, and also you can have a convenience function that sets both of them. So what are the benefits of doing this? So by having these access methods, we can actually hide implementation here from the user of the object. So for example, if the points are stored in a relational database or on some website, we can implement set X to take the X, write it to the database. So we can hide the implementation here. The user doesn't have to know about how it's implemented by hiding these internal attributes. So now we have to access the class a bit differently. So now we create our object. We can set a position here with the set method, set X, set Y. Of course, we need a way to actually show that the user can access these variables. So usually that is done using functions as well. So we have an X function and a Y function that returns these internal attributes. So running this again, we can print actual internal variables here by calling these functions. Print X parenthesis Y. So we use function for setting internal values and also accessing them. So now we have created a class that completely hides the implementation of the underlying variables, hides the implementation. So what we can do now, we can actually change the implementation of point to actually store them completely differently. And we can still use this code unmodified. But somehow, I think the way of assigning attributes that I showed you at the beginning, p.x equal to something, that is a very simple and powerful way of assigning things. And Python enables you to go from this simple way of assigning attributes to encapsulated version of that without actually needing to use set and get methods for the user. We can use something called properties. And if we have our existing class here with a set x, set y, set get y, we can define properties x and y. And instead of define this keyword here, the first parameter here is the method that is used to return a variable value. And the second one is what is used to set them. And now we can access both of them just like they were attributes, directly accessible. So what happens if you type x equals to a value, it will call set x. If you use the x variable somewhere, an attribute, it will call the get x.
One question.
Okay.
Why have you assigned x and y to self twice? 3 times. One after the initialization. Here.
Yeah.
And then over there, the next definition, we assign x to self again.
I mean, why you repeat this one?
Yeah.
Because here you change the variable x. So I assign underscore x to a new one because this is if the user want to change the x value, he calls the set x function and provides a value here for x, which is assigned here again. So for every set, you need to assign it again.
Okay.
Yeah. But now we can use this class completely differently. So you see here, I put print statements here in every set x, set y, and so on. And if we run this example here, we create the point. We do px equals to py equals to, just like the first example when we used that attributes directly. Now we have hidden attributes encapsulated the actual internal implementation, but we still have this nice way of assigning attributes. And we also call here to print out the x and print out the y. And if we run this, you can see here, first it calls set x. This is the one. I assign x here, then it calls set x because that is part of the x property. Then we assign y, it calls set y. Then we print x, it calls get x. It prints py, it calls get y, and then prints out. So the property combines, creates a really nice way of encapsulating variables. That also means that you don't have to think about creating this set get methods until you really need them. So if you want to protect an attribute for the user to pay some set a too high value, you can start by using just a normal attribute and assign that. And then later on, you create a property with the get set method. But the user doesn't have to change the code. It's the same code. So continuing on. Then you need to also use instance methods. So the verbs to act on the object. So what we created up until now is not actually verbs. It's more attribute access and assignment. What we will now do is the point needs to be, for example, be able to be moved. And then we can implement an instance method here. So we define move, we have self. Every function here needs self. Otherwise, we don't know what object we're manipulating. And then dx, dy, and then we just do add to our internal x and y coordinates. Then we do move again. So now we can create 2 points, and we can create p0 move 10, p1 move -5, -5. And you see here that the positions updated when we did this. Another method that can be useful is that to be able to copy the values of an existing point instead of assigning them manually. So copy from method. So in this copy from, we have an existing point coming in here, and then we just retrieve the x value, y value from that incoming point and assign them to x and y. And then we can do copy from, so we create a P1 here, assign that from P0. So now when we print them out, they should be the same. And they are. There are some other cool functions as well. Python contains, we have already seen one of these special functions in Python called init, which is called when you create a new object. There's also a special method called __str__, which is called when you print an object. The object print actually calls this method on the object, str. And it's this method has the responsibility to actually translating your objects into a printable form. Most of the objects in Python already have this str. If you create a new class, you will get the default print str method, which will print out the address of the object in memory, which is kind of ugly. So for example, if I try to print out my object here now, which is a point, it just shows you this kind of ugly message here. If we want it to be print out the actual coordinates of our objects, we need to override and create this str method. So let's see here. I have implemented one str method here. So in this case, I do return a string here. So the str method should print itself. It should return a string that is used for printing. In this case here, point, self x, self y, prints out, returns that string. And if we run that one, we can now, we get a much nicer printout here. So print b here, we actually call this str method, and our own class will return a nicely formatted representation of its own class.
Why do you have plus signs before the string?
Sorry, which?
Why do you have plus signs before and after string?
So if you, when you print with a print statement, you can have comma signs between the strings. But when you want to combine a string, you need to have plus signs. You can't use comma signs. So the plus sign will add the strings together to single string. If you have put commas here, it will have returned a tuple. So
you have one string.
So you have to. So I need to convert it to a string here. So that's why I do str, and then this will become a string, and it convert y to string as well. So the str method needs to be able to, has to return a string. Another interesting thing with classes is that you can do stuff like this. I will create a range of points here. So I will create an empty list here, and I will store a lot of random points in that list. And there are two ways of doing this. This is a more readable version. So I create an empty list, and I loop over 10 times and add 10 points. Then I can also use a simpler form of this. So you can do something called explicit string here. You do point random here for I in range, and that will create a list directly. But what you can do now is you can loop over the points and print them out. And now you can get a nicely printed list here with the numbers here. Yeah, and references work the same way. So every point you create has its own memory area. So these are different here. So if you do P2 equals to P0, they will point to the same object. So P2 will point to P0, P3 point to P1. And you can see here that the first ones are the same addresses. The second one also are the same addresses. So same rules applies to the built-in data types as well as your own classes that you do, objects defined from your own classes. You can also do one of the important things with object orientation that you can reuse existing functionality. So for example, if I want to create a circle, it has some shared attributes from a point. So then I can inherit circle inherits from point. and it inherits the X position. And we add another attribute called radius here, which we assign here. If we have this inheritance, we need to make sure that the first thing we do in the init for the circle is that we call the constructor from the inherited objects. And you do that using the super here. That will return you point, and you call init here on that point with X and Y. So you pass along these values to the inherited object. Then we add methods for accessing the internal radius again. Update our copy from, because we need to also copy over the radius. We provide a circle implement print statement here. And now we can do stuff like this. So we have a P point, C circle. We add radius here, and we have a property here, radius, which we can assign. Both P and circle now have the move method. So for circle, we didn't have to implement the move. That is already provided for us. And we can also print them out in the same way here. Many times, inheritance is, you use it kind of in a limited way, but the most useful thing with you can create classes that compose of other classes. So they consist of, for example, you can have a line that consists of 2 points. So this is a class here that it doesn't have any shared attributes from the point class. So we don't inherit it from point. We have this a separate class, but it consists of 2 points. So it has 2 point objects, P0 and P1. So it's a straight line from 2 points. And we have P0, P1, P0, P1 as properties here. And now we can also decide here if we want to be able to overwrite the positions here. So in this case here, we have get P0, accept P0. That means that you can read and write to the P0 property. We have get here also read and write. But you can choose, if you want to make sure that the objects contained are not overwritten, you can just have a get method. Then you can't write to that object with attribute. So there's a way of protecting access to your object, that you only provide read. So this works here. But if I change here to this one implementation instead, you will see that something happens here. I can't do this. I can't create a new point and assign it to P0. We can only access the object that is already in the pre-provided object. I have to re-execute that one like that. And now it prints out the line. You can also add a method of calculating the length here. So we have a get length here, and we can add a property here that computes the length automatically. So you can print length that will call the get length method and compute the length. So in this case, it will print the length like this. And the final feature I want to talk about is polymorphism. It's a really kind of a bit complicated concept, but it means that if you have a collection of different objects, it will make sure that if you have an inherited structure with the points and circles, polymorph will make sure that it's always the move method of the circle object or the specific object. If it doesn't find a method on the first object type, it will go to the point and see if there is a move there. So let's make sure that you always call the right method. That means that using polymorphism, you can make sure that always the correct method that is called on an object, regardless of the type of the object. So I will create an example here. I have create a list of shapes. I had a point, circle, line, a number, an integer, and a string. And the cool thing is you can do stuff like this. You can do for shape in shapes. And print will always find the correct method to call. For example, the correct str method for the object. So you can see here, every object here in this list knows how to print itself. I have a point, I have a line, and I have my floating point value, and my 42, and my string. So actually, these here, I talked about this last lecture, that floating point number and an integer, they're also objects. They also have the str method, so they know how to print themselves. So that's why you can, if you call print on every object, it will know how to print itself and display itself. So what does 42.0 actually mean, the print statement here? So this is actually what it's called. So 42.0.str parentheses. This is what it's called. And this actually works. So if you run this, it will print 42. So 42.0, the floating point number, is actually a Python object that has a method str. So everything in Python is an object. And now you have a brief introduction to object-oriented programming. Hopefully in the assignment, you will kind of recognize some of the concepts that I'm talking about here. So that I wanted to just give you that introduction before you start working with assignments as well. Okay. Thank you.